Thanks a lot for having me at Mile High Video. My name is Kieran Kunhya from Open Broadcast Systems, and I'm going to be talking about adventures in cutting every last millisecond from latency. So I thought I'd give you a quick introduction. Apologies if you've seen my other presentation at Mile High Video. This is the same slide, but we're a company specializing in software-based encoders and decoders for sport, news, and channel contribution. This is generally business to business. We're based in central London. As you can see on the map, Big Ben is just to my left. You obviously can't see this. Notably, we built everything in-house, and actually, well, we covered quite a bit. Hardware, firmware, software, you name it, it's done. Most importantly, we're not to be confused with the other OBS, the OBS Studio. That's completely separate. So let's look at the problem. Basically, there are two areas known as video contribution and primary distribution. This is getting B2B content, so programs, channels, parts of a program, parts of a sports event, etc., between facilities, be that a stadium and a broadcaster, or a broadcaster and a cable operator. And again, this is for live production, already finished live content. And this presentation will cover things from an operational and also later on a software engineering viewpoint. So, latency. What are the big commercial and operational drivers? There's always operational requirements for lower and lower latency with reduced budgets. There's something known as REMI, or remote production for sports. I'll talk about that later, but that's when you backhaul all camera feeds, audio to one or more locations now for socially distanced production. Didn't used to be that way, of course, but that's one of the reasons. News, there's obviously been a lot of news recently. There's editorial requirements to reduce latency. It's often possible for politicians to hide behind latency and not answer questions. If latency is lower, it's much easier to kind of nail them on topics. And equally on the other side, if there's a contributor who's remote, they have a disadvantage in some kind of debate. So there's really an impetus to get latency down so that people can participate in debates. So yeah, I said I'd cover REMI in more detail. This is when, again, camera feeds are all sent back locally to a facility for production. Now, and this has become obviously a hot topic because production needs to be done socially distanced. It's also been done in the past. It saves quite a bit on flights, hotels, etc. And it also allows a director to go and produce multiple games. But what the director says needs to be reacted upon quickly. And so low latency is required so the director can say something and it can be on their screen in 100, 200 milliseconds. So low latency really matters here. So what's the sort of current state of play in this world? Most of this is based around fixed function specialist hardware, FPGAs, DSPs. They're able to process data with really low latency of 100 microseconds, 1,000 microseconds. But this is specialist stuff. It isn't cheap. We'd like to use more standard IT hardware that will reduce costs and it will improve efficiency. And as I kind of talk about in the other presentation, it allows for much more flexible workflows. But all of this stuff is uncompressed video generally, or at least starts uncompressed. And there's very high data rates, many gigabits. And in software, a lot of this interface is based around SDI, a serial digital interface, as it's known, based around coaxial cables. This is a unidirectional video stream, but it has very low latency. It's about a video line, so it's about 40 microseconds in Europe anyway, 33 point whatever in the US. Plenty of products out there to capture and process these things in software, but the 40 microseconds of latency that you had is abstracted away into frames, so that's a 1,000-fold increase. So usually devices give you a frame at a time. SDKs also hide capabilities of what's actually possible. Is the device doing internal buffering that could increase latency? Is the hardware doing some kind of other processing that takes time? Generally, that's what was once considered offload. But what do I kind of want as a software engineer? And actually, I want the software to do as much as possible, and I want a driver. I don't want an SDK plus driver hybrid that basically every manufacturer has. And on your right, you can see the uncompressed data stream. I want to be able to access this directly. It's 2020. There's no need to offload this stuff anymore. It's very quick, very simple to process. And as I kind of cover in my other presentation, off-the-shelf servers are processing hundreds of gigabits without any issue nowadays. So processing 1, 5, 10 gigabits in software is really nothing. I'd like to start processing the data as soon as a field arrives, not waiting for a whole frame, or even just chunk by chunk, line by line. And I want input output in the purest sense. I want data, and I want to put it on the wire now, not X milliseconds later, not 10, 100 milliseconds later, when the electronics and the driver and the SDK decide it's okay. I want it now. What do you get in reality? Probably the worst case is something like video for Linux and ALSA, where you get audio and video on a separate file descriptor. You can never open them simultaneously, so you're always non-deterministically out of sync. And if you look at some of the very good work done by Karis at Sky from that URL, every millisecond is measured in a live production environment, and you've already lost the game before you've even started. There are also long delays in and out of the SDI card. This can be 2-3 frames sometimes. All sorts of other issues. Sometimes you don't get all the audio tracks because they just don't support it. Sometimes the audio is out of sync for whatever reason and you can't figure why. It's hidden in the SDK. Sometimes you get video down converted to 8-bit because the pipeline doesn't support 8-bit. Sometimes you don't get all the blanking data available because they hide it. You can't change some of the parameters, for example. That does matter in some applications, and so on and so on. The compromise is really bad in 2020. So how do you really solve this? Well, we tried it the hard way. We spent many years building, designing, testing our own SDI card, about 3 years. But we can now fix these aforementioned issues now, and we can actually do this ourselves. And this solves a ton of problems. And I mentioned SDI stands for Serial Digital Interface. Loosely speaking, this is more of a software-defined interface. And we've spent masses of time and at massive expense really for these four lines of code. And I'll go through what these 4 lines of code actually do. It gives you DMA, direct memory access, to buffers of 8,192 bytes. So that's approximately 1 HD line. So that's the 3rd line down. And you get an interrupt every 32 buffers. That means we can now capture, process chunks of video and push out data in the order of magnitude of about 100 lines, sometimes less. But bear in mind, an HD line I said was 40 microseconds, and then we're getting an interrupt every 32 buffers. That's in the hundreds of microseconds timescale. These are really, really tight for a standard service to do. You have to be really aware of thread priorities, CPU power savings, CPUs throttle up and down in the order of milliseconds. So you're already too late often. You have to be really, really careful about this stuff. Actually, handling the bit stream is a big problem as well. Writing this legacy thing. In particular, it has this CRC, a cyclic redundancy check. This is not software centric. So the data is 10-bit, but the polynomial is 25-bit. You can see these numbers are not at all conducive to software implementations. They're not divisible by 8, not divisible by 16, etc. And so we offload this bit. And this is actually one of the few things we do offload, and the hardware does it for us. It's very tedious to build the frame correctly. There's lots of legacy. There's lots of random devices that need a bit to be a particular way for whatever reason. It's very difficult to verify conformance. All the tools are hardware-based. Often we just have to play things out on the wire, but that said, it means we can now fix that situation and do things like unit tests. There's something known as 3G SDI level B. This is where they have an interleaved set of interlaced fields for historical reasons. Some equipment uses this. That's very software unfriendly. And there's a ton of other implementation details that you can ask me about later. But really, what is the goal of this? And the goal is to process lines whilst the next set is arriving on the wire. And this is 100x, 100 times improvement in latency. That is massive. Easily, probably more. But we need to do compression, and we need something, unfortunately, in these times that is friendly enough to send to someone's home or do other things. And I would say in the past that it's been about really squeezing it down to every last millisecond, and I'll talk about that later. But we need something that's a compromise that could get to a home or reasonable office size connection in the 20s, 30s of megabits. And so what we can do is encode a frame or a field at each time. Most equipment doesn't let you receive, most software equipment doesn't let you do it field at a time, so we're already making quite big gains. And so what you do is use something called intra refresh, because these intra frames are really large, and what you do is actually spread them over your GOP. So most of the frame is inter, and then a little bit is intra, and you gradually refresh. And what this lets you do is have a small VBV. So that means the buffering is video buffering verifier is very low. And this is equal to low latency. Unlike intra modes though, intra only video, it is still at the moment best, probably in my opinion, to allow the rate control to work on the entire frame. So you still, in practice, need to receive a field or a frame, and then make a decision, then start putting it on the wire. I would say there are some vendors doing subframe, which is quite interesting, but there are compromises. And what's also interesting is your audio compression actually becomes longer than your video compression. It takes longer, it has a higher latency. So essentially you have to use uncompressed audio, or you could maybe use a codec like Opus in its low delay settings. The other interesting thing is, compared to what we're doing now, there is no compression efficiency difference, because all we're doing is receiving something quickly, processing it quickly, and sending it out. We're not trying to let rate control do subframe yet. So actually we're not losing any compression efficiency hit towards the way it was done before. We're just improving the pipeline, but the inherent encode delay is still the same. So the next thing we can do is actually think about this. And this is going to sound silly, but the way things are done normally is a frame arrives and you have to wait one frame period, and then you give it another frame period to decode. But what happens if you could just decode the slices as they arrive at the destination? And this is what this diagram is trying to show. These slices of compressed data are arriving on the wire, and they're being decoded as the next one arrives. So that means by the time you've got to the last one, you're basically done. This is obviously a little bit tricky. You've got to have independently decodable slices. What this means is you avoid deblocking on slice boundaries. This is x264 slice threads mode. You have issues with high bitrate streams because you have a latency throughput trade-off. You may want to actually buffer the odd slice here or there, and decode them in parallel so that you can use threaded decode, because otherwise you may not have enough throughput to decode in real time. In FFmpeg, there's an API call to do this. AV codec flags 2 chunks. And so you're basically done when the last frame arrives. And so as a result, you can reach 3 to 4 frames end to end. So it's about 64 milliseconds at 1080p59. And you're already making big wins compared to what say a device like a browser or a set-top box or just a normal receiver is doing, because you can encode the data, get it on the wire as quickly as possible, get it decompressed as quickly as possible, and then get it onto the SDI cable as quickly as possible. This is a sort of big win compared to existing environments. So there's also chunk-based encode and decode. All of this, we've left the bitrate roughly the same, and we haven't changed picture quality too much because of the bit exact decode of H.264. But some really high-end applications demand lower latency. This, in my opinion, is not a great idea for H.264. I believe it is still possible. The rate control would like a full frame. But there are codecs out there like JPEG 2000, VC2, JPEG XS that operate on chunks and slices. I've not seen any sort of limited use of this, but because we can now capture, I don't know, 100 lines at a time, we could encode that and send it out. So actually what's possible is capturing, encoding, decoding, and rendering before the frame has even finished arriving on the wire at the source. So you're already starting to rebuild the frame as it arrives. And this gives you of the order 10, 20 milliseconds latency, to the point where it's imperceptible except to experts. But this is really useful for something like a concert video wall, something like VR in particular, where interactive applications are needed. So let's kind of see what happens. It's pretty simple. Source receives a chunk, sends it on the wire, and whilst it's arriving on the wire, it's being decoded, and then over the network, it's being decoded and put on the SDI cable. But this has a huge bitrate penalty. We're now talking in the hundreds of megabits, and it also requires a high-quality network, not necessarily something that's private where there isn't jitter. Say you have a couple of milliseconds jitter, your chunks already arrive late. You need a network that's capable of handling this. in the end, what are the conclusions? In the end, you could kind of have the best of both worlds. You can use IT hardware, but still have subframe encoding and decoding for interactive applications. The example on the right shows 5 frames. As I kind of mentioned, you can get lower, 3 or 4 is possible now since that picture. But it's a substantial effort to get capture hardware to support low latency, to the point where we did it ourselves at considerable time and expense. But in the end, there are big commercial and operational improvements through lower latency, and the end just does justify the means. And now I believe it is time for questions, so I am happy to take some.